In this section, we are going to look at elements, compounds, how they're organized on the periodic table. We're going to explore some of the distributions of metals, nonmetals, and metalloids on that periodic table and understand and think about how those are organized and why those different elements that create everything that's around us, how they're organized on the periodic table and what we're looking at. So this is also, we're going to get into chemical compounds and formulas and understanding chemical names, and it's the basis for our ability to talk about and discuss chemistry. So what is chemistry? What do you think? How is it discovered? How do we study it? Those are some of the things that we're going to talk about in this chapter. So one of the things that I want you to do is I want you to think about what do you think it is? How do you think that you would define chemistry? So I'd like you to take a moment here to write on a piece of paper or type on your computer, what do you think, how would you define these three different areas of science: chemistry, biochemistry, and physics? So take a moment. I'm gonna pause here, but pause this slideshow, and then we'll begin after you've had a moment to think about that. So for me, I really think of chemistry as the study of matter and how it interacts with itself in different forms. And looking at biochemistry, that's really looking at the chemistry of living organisms. So things that are associated typically with what we would refer to as a cell. So a group of something that can, and that's a whole different discussion. What is a cell? What is life? But that's basically the chemistry of life. And then physics is the study of movement, the movement of matter is really what physics is about. So we're going to kind of use all of these things in this class, and we're going to talk about these different aspects. We need to use physics because it helps to explain chemistry. So it's really, again, chemistry is the study of matter and how it interacts. And part of understanding how it interacts is its motion and its movement. We're really going to think about what is matter, and really it's anything that has mass and occupies space. So matter is, so how much mass an object has is going to be what matter is, and that's an inherent characteristic of matter. Weight is a force which objects attract that force by gravity. So before, I asked you to come up with understanding, thinking about what those different things are, but we're going to, if we're looking at matter interacting with itself, mass is an inherent property. So it's something that's part of that compound, no matter where it is. Weight is that difference between, for example, us sitting on Earth. Earth has a certain mass, we have a certain mass, and the weight is actually that interaction between these are two objects. So me as a person with a certain weight, and the Earth has a certain weight, and I'm attracted to that. So if we go to a different location, if I go to the moon, my weight is going to be less on the moon than it is on Earth because it's relative to what I'm next to, versus my mass is always the same, for example. So we're going to talk about the atomic theory. So it's the most significant theoretical model of nature. It's something that allows us to understand that everything can be broken down into smaller bits. So tiny submicroscopic particles. They make up all chemical substance. They make up everything in our world. So this was kind of figured out and thought about in terms of if you try to fold a piece of paper and it gets smaller and smaller and smaller, infinitely small, how far can you fold it down, or how long can you cut it in half, in other words. So that's something that we're going to look at, how kind of digging deep into how small can we get these bits. So we're going to talk about the historical ideas that came about in terms of what led to us looking at matter and trying to understand more about what surrounds us. So there's some important ideas that led to the atomic theory, and one was the law of definite proportions. So this law is, we're basically in a given compound, the elements are always combined in the same proportion by mass. So for example, we'll always find 1 gram of hydrogen in water and 8 grams of oxygen in water. So that is always, you're always going to find the same. It's not like different one day and then the next day water is made up of something else. Those compounds always make up the same number of atoms. And also there's the law of the conservation of mass, which means that when a chemical reaction happens, that matter, that starting point material is still there, and it still has its same mass. It's just maybe organized differently. So there's, again, if we take a closed vessel with 16 grams of oxygen and 2 grams of hydrogen, that'll weigh 18 grams. But then after water is formed, that'll still be 18 grams of water. It doesn't go to 16 grams of water, for example. That conservation of mass, no matter what form it's in or what orientation or what other things it's combined with, it's always going to be the same. And next we're going to talk about Dalton's atomic theory. And now we're going to talk about his hypotheses and what he discovered or what he thought. Now I'm going to tell you off the front end that not all of his theories were correct or are correct. But again, this is how we came historically to the understandings that we do today. So John Dalton was an English scientist, and he worked around in the late 1700s, early 1800s, thinking about matter. And these were his hypotheses. We'll see in the future which were and were not correct, or maybe you already know. But one of the things that he determined was that all matter consists of different particles called atoms. In any sample of pure element, all of the atoms in that element are identical in mass and other properties. The atoms of different elements differ in mass and other properties. So if it's a different element, it's a different mass and it has different properties associated with it. And then when atoms of different elements combine to form compounds, new, more complex particles are formed. So different elements are formed when we rearrange those. However, in a different compound, or in a given compound, the constituent atoms are always present in the same fixed ratio. So we'll talk more about what that means. And then atoms are indestructible. In chemical reactions, atoms rearrange, but they do not break apart. So those are his hypotheses, and we're going to talk about and explore these hypotheses in this lecture. So those were Dalton's hypotheses. So one of the things I want to do is step back here, and I want you to think about why develop a hypothesis? What is the value of that? And how is a hypothesis different than facts? So take a second, take a moment to actually write your thoughts down and think about this rather than just moving on to the next part of the discussion here. At least minimally pause and think about what you think about this question. When we're talking about a hypothesis, remember when John Dalton created these hypotheses, he didn't know that atoms existed. That wasn't a fact at that moment. They were his theories, and these were predictions made by examining other information or data that seemed at the time to make sense to be true. But they were still unsure how atoms were really organized. We have different charges separated, or plum pudding where you have different elements of atoms. They didn't really know how these things fit together or how they work. Then he had these hypotheses, and then they went to start to explore them. How do we test those hypotheses? So really, why do we develop a hypothesis? It's to have something to test. It's to have something to try to prove or disprove so that we have something to aim for. And so one of the first experiments that was done is thinking about testing this atomic theory, what they wanted to do was to see if atoms existed, or that there were things that were made up of atoms. What they did is they had a particle emitter, an alpha particle emitter. So this little box here demonstrates that which had some sort of energy emitting from it. And so that energy, what they found out was if they had a compound in this box and they had a slit in the box, it would expose film. So they would put in the old-fashioned kind of, you can think of the Kodak film, sort of like that. It would be exposed. It would have this like dark black line that would be exposing that film. So the question was, if we put something into this space here, what's going to happen? So one of the ways that John Dalton's his hypotheses were examined was through Rutherford's alpha scattering experiment, where this is kind of what I'm showing you is exposure. So this would kind of get darker and expose the film. And what they wanted to do to test this was to see what happens if we put some gold foil in here. If we put gold foil in, that's really thin piece of foil, what would happen? So pause again here. Think about what's your hypothesis. What are the possibilities? One might be that it bounces off. Maybe it goes through. Maybe something else happens. What do you think is going to happen? What else do we want to do? Are there controls? How do you make sure the experiment's better? So even if we find something with gold foil, do we want to use tin foil, aluminum foil, silver foil, lead foil, a lead block? What else do we want to test in here? So now I'm going to show you the results of this experiment and what they actually found. And when they shot this alpha particle, it's basically an beam of energy, light, and it ended up, some of it did bounce back. A small amount of it did bounce back. Some of it was refracted a little bit to the sides, but a vast majority of it went straight through. And because of this experiment, it was determined that most of what makes up an atom is thought to actually be open space. Since a majority of this energy got through that foil, the thought is that basically where this was bouncing off was just a small proportion of what actually makes up this element. So it doesn't seem to be as dense. It wasn't a solid thing. It actually was somewhat kind of had holes in it. So more alpha rays passed through the gold than were deflected. So this gave us this current view of the atom, where we kind of have this open space. There's still something keeping all of these more dense parts together, but since most of it came through unimpeded, that tells us that a majority of this is kind of open space where energy can flow. So then now we have this new hypothesis that that majority of an atom is kind of open space. So what other variables can we test? And again, I mentioned, hey, maybe having a different type of foil, putting something more thick through there, maybe adding a piece of film, extra gold film in there, spacing the gold film out. So all of those things might change what happens and can improve our ability to understand more about this system. So as we begin to refine our understanding of what this looks like, now another scientist, Michael Faraday, had the hypothesis that maybe these are charged groups. Maybe because of some understanding of electricity and how these things work within, maybe some of these things are made up of positive and negative charges. And let's look at that a little more closely. And so he developed this idea of looking at electrical properties of atoms and the positive and negative nature of the different components. So here we have the anode here is negatively charged, and then this is attached to a battery, and then we have the cathode, the positively charged element. So in this tube, this is basically a glass tube with two positive and negatively charged ends, electrodes, and inside this was a gas, so a different type of gas, And what they found was that this gas was able to glow and conduct electricity, or allow electricity to flow through, or negatively charged elements. Now what we find out is, what is this? This is actually an electron allowing electricity to flow through. So there's a little bit more refining. Okay, so there must be in different elements, in different compounds, there must be this kind of positive and negatively charged group of things. So let's look more closely at that. So the next step in more further exploring this idea of positive and negative charges of atoms and what makes them up, cathode ray tube was developed. And basically what we're doing here is there's again a gas that is charged in here between an anode and a cathode, so a positive and negative charge. And what's happened is that a atom is accelerated through this region that has a hole in it, and it's accelerated through this area. And then what happens is, because it's now charged, it with a magnet, it's actually pulled. So they wanted to see if where it was pulled towards the positive or negative side. And then again, on this end, what you're not seeing, you can have another detector that's detecting where this beam of energized compound has gone to, and determine if it's being attracted to the positive side, being attracted to the negative side, or just not attracted to either and just going straight through. So this allowed some of those to flow through and have a little better determination of what's happening. Now the other thing that they could do with this, depending on how much it's pulled towards the positive or negative charge, we could define how heavy that is, how much mass is there. Because again, you kind of think about, if I have, for example, a bike, right, and I have a rubber band kind of hooked to the bike, or a bungee cord, I can pull on that person on the bike and they're going to come to me pretty easily. If I attach that to a truck, I pull that rubber band, nothing's happening at all, right? So the less that something moves to a positive or negative, and depending on the strength of that charge or that magnet, gives me an idea. You can use that to determine the mass of that compound. So I'm going to show you a quick video to see what that looks like in real life. Here's an example of that kind of anode array tube. Here's an example of that type of anode array tube. And here's an example of a magnet deflecting that ray of energized light. So modifying the cathode ray tube from the original one that was more simple, that just was kind of shown in that video, to this one where we can kind of push this through and determine the mass now based off of the strength of the magnet and the size of the thing that's coming through here. They're able to determine that an electron actually has some type of mass. This is really the foundational work for what we now use and call the mass spectrometer. So we use this to detect different elements, and we look at its ability to come through something similar to this, and the mass of it's determined by how much it's reflected by the magnet. And so the higher up it is or down it goes, that's going to tell us the size of the compound coming through. So again, you kind of think about it this way, in a little different way than I mentioned before. Think of two objects of different sizes, and like a car and a bicycle, for example, or a truck and a bicycle, semi-truck. And then if you throw a tennis ball at each of them, what is going to happen between if you throw a tennis ball at a bicycle or a car, right? So you can think the thing with the smaller mass is going to be influenced more and have probably a change in trajectory more for the thing that is smaller. The thing that's bigger is just going to keep on barreling through that impeding force. So I mentioned before that was a foundational experience. That other cathode tube was a foundational understanding of that we have something in our atoms that are negatively charged. And I mentioned it was a foundation for making the mass spectrometer. And so this is where now we discover the proton, and this is the mass spectrometry, the Rutherford lab in 1918. So about 100 years ago, they were able to then look at, basically have this front end compound which stripped off electrons from a substance that's entering this area. And then what happens is we knock off those negatively charged electrons, and then we pass this through a negatively charged condenser that keeps this flow of ionized compound through here. It's changed through, this trajectory is changed by this magnet. Different magnetic powers are applied to here, and then it hits a detector. And that detector tells us how much that thing weighs. And so this is basically where they were able to identify now that the strength of the magnet that had to be applied was much, much more, about 1,800 times more than the strength for the electron, which tells us that that hydrogen mass, it was equal to that. So it's 1,800 times the mass for a proton than it was for an electron. So masses of other gases over whole numbers of multiple times were looked at and analyzed and detected through here. So once we had an idea of hydrogen, for example, or helium, they could start to kind of get more and more information about the system, about the elements that make up our universe. So they found that the smallest, the proton, was the smallest positively charged particle in that system that made up hydrogen. And then helium would have 2 of those, and then we keep going. These experiments that I just spoke about help us to understand the atom and how it's organized. First of all, remember that scattering experiment where we had the alpha particles and that gold sheet, that gold foil. The nucleus, now, we know because of that experiment, there is a tight grouping of most of the mass of the atom is smack in the middle of that element. And it has all of the positive charge based off of what we know from some of the other experiments with the mass spectrometer. And it doesn't take up that much space. It's a very small volume at the center of the atom. Very tiny, extremely dense core of the atom. And so this is different than what maybe we had thought in the past. So there was another kind of jelly model, the one on the right, where initially people thought there was just kind of positive, negative charge within the elements, and they're just kind of separated out, evenly distributed throughout the atom. That Rutherford scattering experiment helps us to know, okay, these positive and negative charges within that element are really focused, the positive elements are focused right in the middle, in one little dense core, and the negatively charged electrons are flowing around that core, but they're attached somehow. So these experiments suggest the model on the left is the proper model, the proper hypothesis for what is now supported by the evidence and the experimentation. So what we know from some of these experiments are there are really 3. So we started with an atom, but we actually found out that there are subatomic particles. There are things that atoms are made up of. And there are 3 primary subatomic particles that we need to know for this class and need to understand. One is the electron, and that's that negatively charged element. So you can see this chart here. I'm going to tell you the electron. It has the mass of 9, approximately 9 times 10 to the negative 28 grams. So really, really, really tiny. It has a negative charge. And then if we look at the atomic symbol for an electron, we have an E for electron. It has basically the size, so that we put that up here for atomic symbols. The size of this is almost 0. It's 9 times 10 to the negative 28. So we say it's really, really, really tiny. And then it has a -1 charge. So this is going to be the basis for that. Atomic symbol is the name of the element, the size, and then the charge. A proton, on the other hand, 1.6 times 10 to the negative 24th. Now, still really, really small, but, right, multiple orders of magnitude bigger, right? This is negative 28, that's negative 24, that's 4 whole units, right? That's 4 whole spaces on the digits. So this is a lot exponentially bigger than an electron. And it has a positive 1 electrical charge. So we have the symbol for this is a 1. The size is a 1. It's, even though it's really tiny, it's given the 1 on this atomic mass units of 1, and the positive charge here. You can also say it's a proton, which has a 1 and a 1. So it's kind of this similar thing. Hydrogen is the same as just a proton. A neutron, on the other hand, has a very similar mass. Not exactly the same, but pretty close. And the electrical charge, however, is non-existent. There's no charge on a neutron. So this would be the atomic symbol for this. It would be a 1 for the mass, because it's similar to the proton, which we consider also. So a conversion factor would be 1.673 times 10 to the negative 24th is equal to 1 atomic mass unit, and that's how we're grading these. And so then the neutron is very close, so we give that to be 1 atomic mass unit, no charge, and then N for neutron. So electron, proton, neutron, so that's what those symbols mean, and that's how that works. So really, I want you to draw something out. I want you to draw a simple element. So look at a periodic table, pick an element. How would you draw that? What do you think going into what we're going to talk about in a second? I just want to kind of I want you to make a hypothesis based off of what we know so far and maybe what your understanding is currently, and then we'll kind of go through and see, hey, later on down the road, was that correct or not? So what do you think? How would you draw your element, whatever element you want? How would you draw it to make sure that you're distinguishing it from other elements on the periodic table? What makes one element different from another? What is an atom? What's an element? What's the difference between them? So I want you to think about that and write that down. I'm going to now pause it and stop this here. This is a good time to kind of take a little break, and we can come back and discuss this and come back to your writings and your thoughts on this to see if your hypothesis was correct and if you need to update this drawing or update your thoughts on what these mean after we've had a chance to kind of go over this and understand this system a little better.